Hello everyone, I'm Kenta Yamada from Okayama University in Japan. I'm glad to have a chance to talk to you. The LLC converter is attracting attention that can replace the back-type converter. However, conventional control has unstable characteristics. So today I'd like to talk about a new control circuit that can improve output stability. Then, let me begin my presentation. Recently, data centers have been facing increased demands for high efficiency and high power density. This is conventional power system. This system provides power to the server rack at 48 voltage DC, and then converts the voltage to stage and supply to the CPU. In contrast, I expect this system in the future. This system provides power to the server rack at a high voltage DC like a 380 voltage, and then converts the voltage one stage and supply to the CPU. The advantage of this system is high efficiency with small current and high power density with a one-stage conversion. Here, I consider that the circuit topology of this converter. Conventional back-type has limited conversion ratio. In contrast, LLC converter have a high conversion ratio, so the voltage can one-stage conversion. Therefore, in this system, the high efficiency and high power density can be expected by LLC converter. However, the conventional LLC has problems when load fluctuations, so now I explain that reasons. The back-type control system is here, and it controls VO with duty ratio. And here is a board plot. As you can see from this figure, the characteristics is independent on RL. Moreover, the phase delay is below minus 180 degrees. Therefore, the back-type has potentially high stability. That's why the controller can be designed with fast response. On the other hand, the LLC control system is here, and it controls VO with operating frequency. And here is a board plot. As you can see from this figure, the characteristics depend on RL. Moreover, the phase delay is over minus 180 degrees. So, the LLC converter has potentially poor stability. That's why the controller has to design for worse RL conditions. Because of the above reasons, when load fluctuations occur, the back-type has fast response, while the LLC has a slow response. To address this problem, in previous study, the power factor control was proposed. So this slide explains the difference between conventional control and power factor control. The next slide is about conventional control. Conventional control output low voltage at high frequency and output high voltage at low frequency. On the other hand, in previous study, the power factor control is controlled VO with cos theta. Theta defines as the phase difference V inverse and I1, and shifting theta based on cos theta to adjust effective power. For example, at large theta, the waveform will look like this. In this case, input the small effective power and output low voltage. In contrast, at small theta, the waveform will look like this. In this case, the input large effective power and output high voltage. Next, I explain the advantages of adjusting effective power with cos theta. In the case of an LLC, controlling the cos theta shifts the phase angle theta, which also changes the effective power. Accordingly, the effective power P is expressed by this equation. In other words, effective power can be adjusted regardless of RL conditions with cos theta. Similarly, in the case of the back-type converter has stable characteristics, the effective power can be adjusted by controlling the duty ratio. Accordingly, the effective power P is expressed by this equation. In other words, effective power can be adjusted regardless of RL conditions with D. From these reasons, cos theta and D can be considered similar meaning parameters. Therefore, the LLC with power factor control would have stable characteristics like a buck-type converter, and controller can be designed like a buck-type converter. However, the power factor control is just a concept, which means actual circuit of power factor control is missing, and no experimental evidence of stability improvement. Therefore, the purpose of this study is propose the power factor control in actual circuit, and then verify the performance in experiments. First of all, I'll explain the approach and requirements of power factor control. These are the main waveforms: inverter voltage, primary current, the resonant capacitor voltage, and the power factor angle theta show this part. Then I consider the step required to shift theta. The first step is to detect reference phase. The second step is determine phase shift value from reference phase. The third step is rising shifted gauge signal. Thus, if I change the phase shift value, it can shift the theta. Here about first step, it is difficult to detect the peak of the current. In contrast, the zero crossing point of the resonance capacitor is easy to detect. So, reference phase is determined to VCR zero crossing point. Therefore, it requires VCR zero cross detector and shifted gauge signal generator to implement. Next, I consider requirements of second step. These are main forms for each cos theta. In the case of cos theta nearly 0, this ratio is nearly 0. In contrast, the case of cos theta nearly 1, this ratio is nearly 1. From the reasons, in this study, I'll approximate T phi as a quarter of the period multiplied by cos theta. Therefore, it requires operating period T detector and multiplier to implement. Here I propose control circuit diagram and follows the approach and requirements just described. It contains 4 function blocks. The first is the VCR zero cross detector. The second is the time to voltage converter to detect operating period. The third is the phase shift value calculator. The fourth is a gauge signal generator. From the next slide, I'll explain the detailed circuit of each block. First, I'll explain the VCR zero cross detector. In this circuit, the resonant capacitor voltage is detected by a capacitor C sense larger than the resonant capacitor CR. Then the comparator detects the falling zero cross timing VCP, and the mulch vibrator detects the falling timing V0. Therefore, this circuit can detect the phase shift timing reference. Secondly, I'll explain the time to voltage converter. It is charging a capacitor from a constant current source causes the voltage to rise with a constant slope. Then resets the capacitor voltage by V0 to generate saw wave. Therefore, the voltage Vt detected by the peak hold circuit is indicating the operating period. Thirdly, I'll explain the phase shift value calculator. The Vt phi is a quarter of Vt multiplied by cos theta and calculated with an analog multiplier. Besides, Vf indicates the timing of the falling edge, so add a half of Vt to the shift value Vt phi. Therefore, this circuit can shift Vt phi and Vf by changing cos theta. Finally, I'll explain the gate signal generator. This circuit compares the generated saw wave with the Vt phi and Vf using a comparator. Then, the result of each comparison are calculated with AND logic. Therefore, this circuit can generate the gate signal with shifted by T phi and 50% duty. Finally, are the experiments to verify the effectiveness of the power factor control. Initially, organizing the experiments. The first compares back type and power factor control. The experiment evaluates a board plot of control value to VO to confirm similar characteristics. The second compares the conventional control with the power factor control. The experiment evaluates the board plot of control value to VO to confirm stability. Then evaluates our output impedance to confirm low impedance. Besides, the experiment circuit is shown in this figure. Here is the experimental result of compares board plot of control value to VO. The orange plot represents the back type and the blue plot represents the LLC with power factor control. As can be seen from this figure, the two types have similar DC gain, similar gain slope, and similar phase delay. In addition, this part of the difference is thought to be due to the damping factor. Therefore, it can be confirmed that the power factor control has the similar control characteristics as the back type. Now, the next experiment. Here is the experimental result of compares board plot of control value to VO. The left figure shows the result of conventional control. As can be seen from this figure, the conventional control has different DC gain and crossover frequency for each RL conditions. In addition, it has significant phase delay. And then the right figure shows the result of the power factor control. As can be seen from this figure, the power factor control has almost same DC gain, crossover frequency, and phase delay for each load conditions. In addition, the phase delay is moderate. Therefore, it can be confirmed that the power factor control has robust characteristics against RL fluctuation. Now, the final experiment. Here is the experimental result of compares output impedance. The power factor control is shown in warm colors and the conventional control in cold colors. For this low frequency area, the power factor control has a lower impedance than the conventional control. Therefore, it can be confirmed that the power factor control has high output voltage stability. Finally, here is a summary of this study. In this study, I propose the power factor control in actual circuit and verify the performance in experiments. In conclusion, it confirms that the proposed control has a similar characteristics as a back-type converter, and it has robust characteristics against load fluctuation. In addition, it has low output impedance and high output voltage stability. My presentation will end here. Thank you for your kind attention.